Welcome, my friends. I'm so excited because in this video, we get to talk about the chi-square test of independence. So let's go ahead and get started. The first thing we need to do is discuss the chi-square distribution. Now, a couple of notes. This is pronounced chi and not chai and not chi. It is the chi-square test of independence and the chi-square distribution. And it is represented by a letter that looks a lot like an X, but is actually the Greek letter chi. So this is kind of like a little fancy X, and it is squared. It is the chi-square distribution. Now this is a skewed right distribution, as you can see from the picture, so it kind of tails off towards the right. And the distribution only takes on positive values as it consists of squared numbers. To get this distribution, you end up having to square something. And since when you square numbers, they can only be positive, this distribution will only contain positive numbers. And in fact, it actually starts right at 0. So the starting point of this distribution is 0 and then goes kind of forever up into infinity to the positive numbers. Now, exactly what the shape of this distribution is changes based on something called the degrees of freedom, something we've talked about, and kind of a similar idea to the t distribution. Now, the way that the degrees of freedom are found is a little bit different than the t distribution, so we'll briefly talk about that later, but it turns out for the way that we're doing the test, we don't even really need to know the degrees of freedom. All hypothesis tests that are performed with this distribution are going to be right-tailed tests, so we never have to worry about anymore when we're dealing with this distribution, is it right-tailed, left-tailed, or two-tailed? We're always going to be doing a right-tailed test, meaning we'll be finding a probability in the right tail of the distribution. Now, this distribution is used for a number of different hypothesis tests, but the only one that we're going to do here today is what's called the chi-square test of independence. So the purpose of this test is to determine if two variables are either independent or dependent of each other. And what is meant by independence would really just mean that the outcome of your first variable doesn't have any impact on the outcome of the second variable, and these variables would be collected for the same individual. So independent variables would mean, it doesn't really matter what the observation is for the first variable. It doesn't really tell you any information about the second variable. So the example we're going to use here are, we're going to ask the question of if BMI and dementia are independent in individuals who are over the age of 65. So it turns out what you'll need to do for this, if you have a quantitative variable like BMI, body mass index, is kind of split it into what we call levels or classes. So that's what we have here. We have like less than 20 BMI, 20, 25, 25 to 30, and greater than 30. You'll never have to do this. This will be something that I will already have done for you in any problem. And then for dementia, you could maybe think of more than two possible levels, but I'm just going to use yes or no. We could have like early onset of dementia or something, but I'm just going to say either yes, we've classified someone as having dementia, or no, we have not. So what would it mean for these variables to be independent or dependent? Well, if BMI and dementia were independent, that would mean that individuals of all BMI levels experience dementia in about the same frequencies. Right? So it doesn't really matter if you're part of the less than 20 or the greater than 30. It doesn't really matter which BMI classification you're in. That doesn't really make it any more or less likely for you to have dementia. On the other hand, if these variables were dependent, then that would mean that someone's BMI is going to tell us some useful information about how likely they are to have dementia, right? It might be the case that people who are greater than 30 BMI are more likely to have dementia, or maybe the opposite, right? So that's what we're saying when we say dependent, right? That would mean that certain BMI levels are either more or less likely to have dementia. And that's kind of the whole purpose of this test. We're going to want to see if our two variables are either independent or dependent. So the data in terms of a problem like this will be given in what is called a two-way table, or sometimes called a contingency table, which kind of gives you the cross sections of these two variables. So we have one variable on the rows, which in this case is the BMI, and then another column on the columns, which is the dementia. On the inside, we have kind of the intersections of all of those. So like, for example, there were 30 people who did have dementia and were less than 20 BMI, etc. For all those, we have the total of yeses, which are 400, total no's, which are 4,600, and then the totals of every BMI classification, and the grand total, which is 5,000. Now, the null and alternative hypotheses for this test are a little different than some of the tests that we're used to, in that we're going to write these out as kind of a short sentence. So the null hypothesis should always be that whatever variables are on your rows and columns of this table are independent. And your alternative hypothesis should be that those two variables are dependent. So literally, your two hypotheses are exactly the same, with the only change being that word from independent to dependent. But of course, you're going to be more specific to your particular example. So you're not going to just say the row and column variables. You're going to specify what those variables are. So in this case, the row variable is going to be BMI classification, and the column variable is our dementia, right? So our null hypothesis would be that BMI and dementia are independent, and our alternative would be that BMI and dementia are dependent. Make sure you have independence in the null and dependence in the alternative. If you switch these around, it is technically not correct. So make sure you have that straight. Here are the assumptions of the chi-square test of independence. First of all, there must be two categorical variables, each with at least two levels. Now, this is a little bit of a loose assumption because as we just saw in the previous example here, we can sometimes use quantitative variables, but we have to split them up into levels like we did in the previous slide, right? So BMI is a quantitative variable. It's not a categorical variable. But as long as you kind of split it up into these quantitative categories, it can still work. If that was the case, then sometimes you might want to consider maybe a different test could be appropriate, but you still could do the chi-square test if you split it up into these categories. Second of all, we must, of course, have a random sample. And then something called the expected cell counts must all be at least 5. Let me briefly try to explain what is meant by this. We'll end up calculating these later. But if I went back to this table here, remember that the null hypothesis is that our two variables are independent. And it turns out that if you had the results of the survey, like all the total results, it turns out that if the two variables were independent, the inside of the table would actually be predictable. You could actually predict what every single one of the values on the inside of this table would look like if your two variables were independent, right? And that's all we mean by expected counts, right? So for example, if these two variables were independent, how many people would you expect to see who are less than 20 BMI and have dementia, or in any of these other categories, right? And as long as all of those numbers were at least 5, we could move forward with the test. Once again, we will calculate those values a little bit later with our calculator, but this is one of the assumptions. So let's go ahead and look at an example. So the following table shows the results of a survey where the BMI of 5,000 randomly selected individuals who are age 65 or older was recorded. The individuals were also tested for dementia, and we want to know if there's sufficient evidence to suggest that BMI and dementia are dependent at the 5% level of significance. So the very first thing you should do is set up your null and alternative hypotheses, which we already did on a previous slide. The null should always be independence, and the alternative should be dependence. So the null hypothesis is that BMI and dementia are independent, and the alternative is that they are dependent. At this point, we can go to our TI-84 calculator to plug all these numbers into our, not actually the list. In this case, we're actually going to be plugging them into the matrix. This is kind of a unique test with the TI-84 calculator. It's one of the only ones that you don't actually plug numbers into your lists. We're going to be plugging them into the matrix. So let's grab the calculator, and let's go to second. And then matrix is right here under the x-1 key. And then you'll have a bunch of different options here. You're going to want to scroll over to edit and press enter when you're over matrix A. Make sure it's matrix A. You do not want to edit the other ones because the default later when we run the test is going to be A, and so that you don't have to change it, make sure you do matrix A. So we can press enter here, and it's going to let us modify this matrix. Now you want to set the dimensions of the matrix so that it matches this table that we have here, and not including the totals. You don't actually need to plug in the totals into your calculator, just kind of all the numbers on the inside of the table, right? So that means that we have 1, 2, 3, 4 rows and 2 columns. So I'm going to press 4, press enter, and then 2, and enter, and that's going to modify this so that I have a 4 by 2 matrix. At this point, you can go ahead and type in all the numbers. So that's what I'm going to do now. Just press enter after typing in each one to move to the next. And then once you have all those numbers typed in, you can go to stat. You can arrow twice to the right to get to the test menu, and you can scroll down, and eventually you'll see an option that says the chi-square test. Make sure you don't choose the chi-square GOF test. That's something called the chi-square goodness of fit test, which is not the one we're doing here. We need just the chi-square test. The observed is what we just plugged in. These are the values that we observed from our sample. Expected is what the calculator is going to output as the expected values into another matrix. So once I press calculate, it's going to calculate a new matrix in matrix B, which will contain the expected values. So let's go ahead and calculate. And you'll see here it gives me a couple of numbers. It gives me what we call a chi-square test statistic, as well as a p-value. You're going to want to write down those two numbers. And also it does give you the degrees of freedom. I mentioned before that we don't really technically need the degrees of freedom to do this test, the way that we're doing it at least, because we already have the p-value and we don't really need to use this degrees of freedom for anything else. But I'll just mention briefly how you could find this degrees of freedom. If you take the number of rows in this table and you subtract 1, and then you multiply by the number of columns in the table minus 1, you will get this degrees of freedom. So in this case, the number of rows, there are 4 rows, so 4 minus 1 would be 3. And there are 2 columns, so 2 minus 1 would be 1. 3 times 1 does give you this degrees of freedom of 3. Okay, the other thing I want to mention here is that if we press second and matrix, you should now see that there is something in matrix B. So let's go ahead and edit matrix B, and you can go ahead and see what that looks like. And as I mentioned earlier, this is what we call the expected matrix. These are the values you'd expect to see in your table if your 2 variables were independent. So if our variables were independent, we would expect to see a 32 in the very first slot. Or, down here, we would expect to see a 16. So this is actually looking like a pretty big difference, right? We'd expect that if these variables were independent, we would only see, we would only see 16 individuals who were in the greater than 30 and yes kind of a matchup here. But we actually saw 30. So that's almost double what we would expect to see. So that's seeming to be pretty good evidence maybe against the assumption that they were independent, because this number is quite a bit larger than we'd expect under independence, right? So you don't even necessarily need to look at the expected values. We should, I guess, technically probably check to make sure they're all at least 5. But this is really how the test would be done if we did it by hand, right? It'd be a comparison of the expected values to the actual values that we've observed here, right? So here's some of the instructions here. And here is that output. And we can kind of envision that p-value on a chi-square distribution. Now I do want to also show you here how you could get this p-value using another function on the calculator. Obviously here they gave us the p-value, but let's just assume that we didn't have this table and we weren't able to calculate this p-value, using that chi-square option there. Well, another option to do this would be to use what is called chi-square CDF. So if we go to second distribution, most likely you're familiar with like normal CDF and maybe TCDF. Those found p-values for other distributions, but now we can use this option 8 here for chi-square CDF. We can plug in the lower bound of 14.17. The upper bound of it's going to be 1,000, because this kind of goes forever in the right-hand direction. Remember, it's a right tail test. And then we can plug in those degrees of freedom. Once again, that's the number of rows minus 1 times the number of columns minus 1, in this case 3. And we can paste that, and we get approximately the same number that we had there a second ago from the calculator, right? It might be a little bit different due to some rounding, because I think I only took 2 decimals on this value, but we do get very close to the same number. So I would make sure that you know how to find the p-value, both using chi-square CDF as well as based on the table and using the chi-square test. All right, at this point, we're almost done. All we have to do is the decision and conclusion. So the decision is going to be made by comparing the p-value to the level of significance. So we had a 0.0027 p-value, which is less than the level of significance of 0.05. So the p-value is low, the null has to go. We're going to be rejecting our null hypothesis. So we can go ahead and write our conclusion. Our conclusion is going to be that at the 5% level of significance, there is enough evidence, since we rejected our null hypothesis, to suggest that BMI and dementia are dependent for these individuals who are over the age of 65. And this is not just a conclusion based on the individuals in this table. This would be a conclusion based on the greater population of, everyone that we, not just the ones that we've drawn from. Hypothesis testing relates to the population and not just the sample. All right, so here is a problem for you to try. The following table displays movie preference by age of 500 randomly selected individuals. We are asked, does the data suggest that age and movie preference are independent? And we are asked to use a 0.05 level of significance. So go ahead and set up your matrix, set up your null and alternative hypotheses, run the chi-square test, get your p-value, make a decision, and then write a conclusion. I do just want to note here that I think that in this problem you may get scientific notation on your p-value, so I want to make sure that you're familiar with that and know how to read that. Let me change this one just to see if I can make it give me scientific notation. So if you get a value that looks like this with like an E negative something at the end, that's scientific notation. That means basically move your decimal place 4 places to the left, right? So this is really actually a much smaller number than what you see, right? It looks like it's like 1.56, but it has the e-4 at the end. So if you shift this decimal place 4 places to the left, you're going to get a smaller number. You're actually going to get 0.000 and then all of those numbers. So another way I could write this would be something like this. I'm not going to write out all the decimals, but it'd be something like this, right? So the decimal place was right here, right after the 1, but now I've moved it 1, 2, 3, 4 places to the left. Kind of a shortcut there is whatever this number is, you can have 1 less 0 is what you're going to end up having in the non-scientific notation expression, right? So instead of 4, I've got 3 zeros here, 0.1230, and then I have that number. And you'll see if I press enter, I do end up getting like a pretty similar notation, right? All right, go ahead and give this problem a shot, and then I will see you in the next video.